Well, good morning. This is 11:36. I'm sorry it's 6 minutes late getting started, but I had a student come by to turn in work and pick up a test and do things. I just didn't have time in between my two classes to get all that done, so sorry, late getting started. But nobody else is in the room, so we will get started where we left off last time. We'll start from the current slide, and we are currently recording. I'll wait and do announcements until everybody, or at least somebody gets here. But where we were last time is Chapter 3, Determinants, 3.4, Applications of Determinants. And we had just talked about Cramer's Rule, set up for Cramer's Rule, and now we will use Cramer's Rule. Example 3, middle of page 130. It says, use Cramer's Rule to solve the system of linear equations. Let me get my pen set up. 4x1 minus 2x2 is equal to 10, and 3x1 minus 5x2 is equal to 11. Okay? Says use Cramer's Rule to solve this. Now, you could solve it as we normally would by elimination by addition. I would suggest multiplying the top equation, say, by -3 and the second equation by +4, and that would then solve it. Cramer's Rule says do it this way, okay? First we'll do x1. x1 is the determinant of your coefficient vector, coefficient matrix, except instead of the x1 coefficients we put 10, 11. So 10, 11, -2, -5. Divided by the coefficient matrix 4, 3, I'm doing columns now, -2, -5. Okay, and these are pretty easy to do. That would be -50 plus 22 is a negative. Goodness gracious, the old gray cells, they aren't used to doing this early in the morning. Okay, -50, and minus 22, that would be 28. That's a -28 divided by, and this one is a little easier, that's -20 plus 6 is -14, so that's 2. Okay? That's your x1. Your x2 is a different numerator. This time we do the 4, 3, the first column, then we put the 10 and 11 there and divide that by, you don't have to divide it by anything, -14. You've already done that. That is the beauty of Cramer's Rule. Once you've done that denominator, you're done with it. It's done. Okay? So the numerator here is 44 minus 30, which I believe is 24 over -14, and that would be -12/7. Now, did I do that right? No, I didn't. -44 minus 30. Oh, it's 14. 14. I can't subtract. And 14 divided by -14 is -1. Okay. -14 divided by -14 is -1. All right. Now, let's check our answers. I'm pretty confident they're true. 2 times 4 is 8. Plus 2 is 10. That works. And 3 times 2 is 6. Plus 6. Whoa! plus 5. I can't add there either, and that's equal to 11. 6 plus 5 is equal to 11. Okay. So sure enough, that worked. Now, is Cramer's rule any easier than elimination by addition? Probably not. Okay. Is it easier than row reduction? Probably not. But what if you had the same set of equations and you're looking for different outcomes? Okay? In other words, you were trying to optimize or do something else, you know, say, well, what if this is the case? What if that's the case? Then Cramer's rule may be easier because you only have to compute, if it's the same set of equations, you only compute the denominator once, okay? And then all you have to do is do possibly a very simple matrix in the numerator, and you've already got the denominator done. And then you can look at many cases with the same set of equations and do some pretty decent comparison. In that case, Cramer's rule probably wouldn't make sense. Okay? Now, it says here, Cramer's rule, top of page 131, generalizes easily to systems of n linear equations and n variables. The value of each variable is given as the quotient of two determinants. The denominator is the determinant of the coefficient matrix. Numerator is the determinant of the matrix formed by replacing the column corresponding to the variable being solved for with, that's a hanging participle there, with the column representing the constant. So, rather than write all that down, well, I guess maybe we should. Okay. I had been thinking we had already done it, but I guess that's right. We only did 2 by 2s. Here's a 3 by 3. I'll try to do it quickly. A11x1 plus A12x2 plus A13x3 is equal to B1. A21x1 plus A22x2 plus A23x3 is equal to B2, and A sub 31 x1 plus A sub 32 x2 plus A sub 33 x sub 3 is equal to B3. There's your system 3 by 3. Okay? And they just chose the third one, x3. You could choose any one of them. What would be the value for x3? Well, you do the determinant of your coefficient matrix, except instead of your coefficients for x3, you put in the constants. Okay, so it's goodness gracious, A11, A12, then do a B1, A21, A22, B2, A31, A32, B3. That's your numerator. Your denominator is your coefficient matrix. Determinant of that. A11, A12, A13, A21, A22, A23, and A31, A32, A33. Okay? Now, just thinking about this, again, 3 by 3s are relatively easy to do. You just repeat the first two columns and do that. And once you do that that denominator once, you don't have to do it again. That's going to be the same denominator every time. So that's done, and then you just have to do the same 3 by 3 reduction of your numerator, but you have to do that all 3 times. So one for x1, one for x2, and one for x3. The denominator, do it once, and then you're done. You don't have to do any more denominators because it's the same. Okay, so that leads then to the general. There is the theorem 311, which is Cramer's rule. We've been talking about it, but I realized we haven't generalized it. Here it is. If a system of n linear equations with n variables, okay, has a coefficient matrix okay, A with a non-zero determinant of A, this is not equal to 0, okay, then the solution of the system is x sub 1 is equal to the determinant of, they call it A sub 1 divided by the determinant of A. X sub 2 is the determinant of A2 divided by A. Determinant of A. X sub 3 is the determinant of A3 divided by the determinant of A. And you keep going dot 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 until you get to x sub n is the determinant of your A sub n over determinant of A. See, every one of those denominators, once you do the determinant once, it's done. And of course you see, sort of by the definition now, I should have said this before too. Before, I think when I did the last one, I started off doing the numerator. Don't. Start off doing the denominator. Because if that turns out being a 0, you don't have to do any more. You know it doesn't have a solution. Okay? And if that A, determinant of A is not 0, then go back and do all the rest of them. And that will be fine. But you really should do the first one first. And the caveat to this is where the ith column of AI is the column of constants. Okay, in the system of equations. The column, the numbers on the right-hand side of the equal sign. All right, they do the little proof there. I'll let you look at that if you're interested in doing the proofs. We just don't have lots of time, so I'm going to move on to example 4, and let's see how it works. So, use Cramer's rule to solve system of linear equations for x. This is minus, to solve it for x, okay? Minus x plus 2y minus 3z is equal to 1. 2x plus z is equal to 0. 3x minus 4y minus 4z, no, plus 4z, I can't see. Okay, minus 4y plus 4z is equal to 2. Okay. I know today is to be a strange day weather-wise. I don't know what's happening outside now, but inside the building, it's gotten cooler, I think, as the day has worn on, or at least in this room. My last class that was in here pretty good sized class. I didn't notice the room was cool. But when I came in from, swapping out my books and came back to the class, and that's after I dealt with that student and stuff, this room felt really chilly. And now it's again feeling chilly. Looks like it's still nice and sunny outside. They said it was supposed to get up to 80 today, so I would guess it's pretty nice outside, but for some reason this room is pretty cold. I don't know why. But anyway, that's beside the point. Just letting you know you are not here to recognize this. So anyway, let me see if I've gotten it written right, because I was missing up signs before, and I think I've got it right. So it says solve this system of linear equation for x. Doesn't say to solve it for the other two variables, just for x. So to do this for x, what we do, x is equal to the numerator is minus 1, no. Oops, I blew that. Okay. Since we're solving for, here goes my voice again. Since we're solving for x, we put the constants in there. 1, 0, 2, and then write the other coefficients as the r. 2, 0, minus 4, and minus 3, 1, 4. Divided by the denominator is your coefficient matrix, and this is your minus 1, 2, negative 3, 2, 0, 1, and 3, negative 4, 4. All right. Now, like I said before, especially if we were going to be doing all three, or whether we are or not, good idea to do the denominator first. Well, I'm going to expand this, span it, using the technique that we did by repeating the first two columns. So it'll be a minus 1, 2, 3, 2, 0, minus 4. And then I'll treat that like it's a determinant, but that's not a square matrix, so it's not. But anyway, you do, that gives you a 0, that gives you a 6. All right, we have a student. Ding, ding, ding. Except it's only true. No, I'm sorry. Okay. I just put a 4 rather than a P. I don't know where that came from. Okay. All right, let's get things swapped out here. Remove the projector. And put the lights. Okay. And as I promised at the beginning when I started talking to myself, I would make the announcements once the student got here. Since Tyrell is here, I'll count that meeting the condition. According to what was published last week sometime, maybe the week before, I don't remember now when, the final exam schedule that they published looks like to me to be wrong. And just one fairly small thing, most of it is absolutely correct, except they have finals starting on Monday, April 29th. And on the academic calendar on the website, on the administrative calendar they published a week or so ago, finals start on Tuesday, April the 30th, not Monday, April the 29th. So as far as I'm concerned, we're meeting in classes on Monday, the 29th. Okay? Now, on Monday the 29th, I have 2 calculus classes and a differential equations class. So they've all got take-home finals anyway, so I don't think it really is going to matter to them. But if you're in some other classes, it may matter. So you check on the Monday, Wednesday, and see when your final is. It should be the following Monday, but, well, it could be that Wednesday. I don't know. But according to this, this is wrong. All right. The other thing that was an error on this, it told us that we needed input grades for regular term students and second mini term students no later than 12 noon on Monday, May 8th. Well, there's two things wrong with that. The main thing is Monday is May 6th, okay? The other thing is final exams are still going on that Monday, May 6th. But on page 3, they then say regular and M2 grades are due on Wednesday, May 8th. So they corrected that there. That was just, I guess, a typo. So can't believe everything you read. Now the next thing, and again, I don't think this will affect you any, but you may know someone it might affect. On the administrative calendar that I mentioned before, the last day to withdraw from classes for full term and second mini term courses is next Tuesday, the 23rd, okay? So if you know of anyone who is hopelessly behind in a class, it's better to get a W than a D or an F, okay? A D and an F hurts you academically, a W does not. Now, I need to make a statement about that too. I think the rest of them I've gone over before. At the beginning of the term, I made the announcement, when we're doing the syllabus, I did it just like we always have done. Syllabi have been like this ever since I started teaching at Lawson. They've changed in other ways, but this has always been the same. Lawson used to count a D and F almost the same. Not quite. The D is technically passing, but Lawson wouldn't give you credit for it. It gives you 1 quality point as opposed to F, which is 0 quality points. So there is a difference between a D and an F, but you still had to repeat a D. And that's what I said in the syllabus. But evidently last fall, and I was out that day because I had a really bad cold and missed the in-service then, and so I wasn't there to hear it, and they acted like nobody else heard it either. They said they made just a really brief passing announcement about changing the D policy. And no one that I've talked with heard it, but they said it, but didn't make a big deal about it. What they're now saying, a D will count for any non-major course. So what is your major? Pre-engineering? Okay. So say if you made a D in Spanish, you could still pass with a D. If you made a D in English, if you made a D, and certain other things. But all of your Area 5 courses, which this course falls in, your upper level calculus, all those courses, now not counting CIS 146, that's in everybody's Area 5, and not counting your PEs. Those you can still make these in. But in what is the type of engineering? Electrical, okay, yeah. I was going to say if you were in computer engineering, they may not want you to make a D at a computer course, but if you have to take, the 251, computer science 251? Okay. Yeah, if you're taking that one, that's your Area 5, you can't make a D in that. The math course is this course, you can't make a D in, so don't do it. Okay, so, yeah. So there is a new D policy there that came as a surprise to everybody. The syllabus, in that respect, is wrong, but...
Will it still be counted on your GPA?
It counts, and it hurts your GPA unless you have a 1.0 average, then it doesn't change it. But hopefully you don't have a 1.0 average, so otherwise it would be hurting your GPA, but you still get to count it as having passed the course. You don't have to repeat it. Okay.
What is the thing? I heard something about make a D, or it might be enough. Make it the school to pay for it the first time, but the second time you'll have to pay for it yourself.
Okay. That's talking about Pell Grant and certain other scholarships, like veterans and things like that. If you're on Pell Grant will pay for a course the first time you take a course. If you either fail it or withdraw from it, they'll pay for it the second time. But they won't pay for it the third time. Okay. If you fail or withdraw the second time, then they aren't going to pay for it again. But you're not on Pell, are you?
No. I'm with student support service, so they kind of help me out.
Yeah. And certain scholarships and other things like this, they may follow those same Pell guidelines. So they'll pay for one retake, but not two. Yeah. So that is a change. Now, what I don't know, they used to say part of the reason Lawson didn't give credit for D's is because most schools won't accept D's when you transfer. But now that may have lightened up some too. It's always up to the receiving school. So maybe, I'll just make up something. It may be that if it's not a major course, that a school like, say West Alabama may take the D, but Alabama might not, or something, or vice versa. So it's up to the receiving school whether they do it or not. So then I would check with the school you're planning to transfer to and see if you're better off repeating the course here or repeating the course there. Your choice. And then to people who, if it's messing up your grade point average better, you can retake the course just to improve your grade point. Okay. Now, what we're doing here is using Kramer's rule, which you weren't here last time, so you probably don't know what it is. Okay. Kramer's rule is a way of using determinants to solve systems of equations. And here's the procedure. And it has to be square equations, three unknowns. Okay. So here's your coefficient matrix. -1, 2, -3, 2, 0, 1, 3, -4, 4. Notice that's exactly what I have here. Okay? That's in the denominator. Okay? Now I just expanded that by repeating the first two rows like we do for doing determinants with a 3 by 3. This only works with 3 by 3s. Now the numerator is not quite the same, but close to it. Because this is, you're looking for x here, rather than putting this column of coefficient matrix, we put that column, our constants column, in that place. But the other two columns are just the same as they were here from your coefficient matrix. Now, I suggest that you first always do the determinant at the bottom, the coefficient matrix first. Because if that turns out being 0, the problem's non-solvable, no matter what the numerator gets you. So always do that first. Make sure that denominator is not 0. Okay? Because if it's 0, you can't. Has no solution. All right. And I had just done, before you walked in, the first downward diagonal, and that's 0. Right? Okay. I had just written this down and drew the line and started to say it. That's 6. Right? You're multiplying those entries together. Right? Multiply these entries together and you get plus 24. Right? Yeah. That's your down diagonals. Your up diagonals are always negated. But the first one's a 0. Okay? So nothing there. Now this would be that it was a plus 4, but because you're going up, it becomes a minus 4. And then the third one is minus 16. You see that? Okay. Okay. And minus 4 and minus 16 is minus 20 plus 24 would be 4. 4 plus 6 is 10. So your determinant of that coefficient matrix is 10. That guarantees this will be a solution. If that was a 0, there are no solutions. Okay? So now we do the same thing to our numerator matrix. I'm first going to expand the first two columns, repeat them. That's a 1, 0, 2, and a 2. Oh, no, I'm not. No, I'm not. Okay? Before you came in, I had already recognized this, and I forgot. Okay? This is so easy to do without expanding because you've got a row with 2 zeros in it. So we'll just take this one here, this 1 here, wipe out that row and that column. First thing you do is determine the position, the sign of that position. Remember, we do plus, minus. That's a minus position, so it's a minus 1 times the determinant of what's left over. Minus 4 minus 4 is minus 8, but you had a minus in front, so this is plus 8. So 8 over 10, which is 4/5. That's the value for x. Now, we can't really check it until we did the other two, but they didn't want anything but the x. But you see, if you got that, that's so much easier than expanding the other way. If you have a row with all zeros except 1, you know that one is. Okay. Let's see what they got. 4/5. Good for them. I feel proud of them all the time. Okay. Now, it's sort of a mystery to me. When they were doing theirs in the book, they said the determinant of the coefficient matrix, A, they write it out and say is equal to 10. They don't tell you how they got it, they just say it's equal to 10. But then, the x then would be the determinant of the top matrix, and then they go into gory detail of how to do that, which is what we did basically. But anyway, you get 4/5. All right. Now that's one application of determinants, solving systems of equations using Cramer's rule. Okay. Here's another. Can I go and erase this?
Yes.
Okay. And this is a bit bizarre, but it's true. You can find areas, volumes, and equations of lines and planes using determinants. And you think, wow, how would that be? Why would that be? Okay? So these are applications in analytic geometry, which is basically what I just described. Here's one. Finding the area of a triangle in the xy plane. Okay? So let's say we have a triangle. Triangles have 3 vertices, right? Okay? And they're all in the xy plane. So this is x1, y1, x2, y2, and x3, y3. 3 vertices of a triangle. Okay? Surprisingly, here's the area of that triangle. Okay? They put a plus or minus in front. Okay? There's a reason for that. Because a determinant could be negative. Areas are never negative. So you use the minus if your determinant is negative, because you have to have a positive. So that's what the plus or minus is there for. But then there's a 1/2. And I can't tell you for certain why the 1/2 is there. But then you do the determinant of x1, y1, 1, x2, y2, 1, x3, y3, 1. Okay? Now notice, you have ordered pairs there for your points, but you have 3 of them, so you have to have a square matrix to do a determinant. So that third column there is just the numbers 1. Now I can't tell you for certain why that's true either, but it is true. Okay? Now, they have a little proof here, and it's a pretty nifty little proof. Okay? They take the triangle in the first quadrant. It's convenient to do that because everything's positive there. Okay? I wasn't going to do the proof, but I will do just sort of a generalized version of it. Okay? Okay. Let's say those are your 3 vertices. There's your triangle. Okay. Now, if you note, if you do a perpendicular down here, a perpendicular down here, and a perpendicular down here, okay? I thought someone came in. Okay. Okay. What we're looking for is the area of this triangle here. Okay? Now I'm going to get some different colors playing here. Let's do this color here. Let's do the area of this trapezoid here. Now remember what an area of a trapezoid is? Okay. If you take this trapezoid we got here between that dotted line and here, okay, and flip it over itself there, then it forms a rectangle because the short side here is up here, the long side here goes here, and you have a rectangle. And the area of the rectangle is the length of this base times the height, which the height is the little side here plus the big side there. Yep, that was it on both sides. Now, the trapezoid, the area of that is half that because you just flipped it over itself, so you got two trapezoids same size, so that would be the area. That's where the 1/2 comes from. Now, the area of this, you're just using this point and that point, and if you did the sum of these two, so it just happens to come out, that's the area of the trapezoid. Okay. Now, you have another trapezoid here. Now, let me pick a different color. You want to pick a color this time?
Let's go blue. Carolina blue.
Carolina blue. Okay. This little triangle here, trapezoid here. Okay. Now, again, if you flipped it over itself, the long side goes up here, the short side goes up here, and you have that triangle, that rectangle, but the area of the trapezoid is exactly half of that. Okay? So if you did those two, you got the two areas of these, the red and the blue trapezoids. But we really don't want all that, so let's subtract off and pick me another color here. Purple. Okay, we're going to subtract off this trapezoid down here, which goes from here to here to there. Okay, subtracting that one away, that leaves the area of the triangle. Right? Yeah. Okay, so that.
So the plus minus 1/2 came from half of the trapezoid or the triangle?
No, okay. The determinant here, when you do this determinant, depends on which order you happen to put these down. Remember, if you change the order, you change the sign. Okay, so if you put these down in other than the optimum order, then this is going to be negative. So then you'll need the minus sign to make it positive again. If that determinant is positive, you use the positive. Because you've got to have a positive area. So anyway, and this hasn't explained where the ones came from, but it comes from the fact that you're subtracting those things and stuff like that. It does work out. But anyway, that's the quick and dirty illustration of how that works. So let's do one, okay? Okay, excuse me. Find the area of the triangle whose vertices are 1, 0, ooh, Carolina blue still. Get back to black. 1, 0, 2, 2, 4, 3. They've stayed in the first quadrant here, which is fine. It will work no matter what quadrant you're in. Even if you span a different quadrant, go across a quadrangle line, doesn't matter. It's still going to work. Okay? So you tell me what the area formula is. Plus or minus 1/2 That's it. Well, you got to figure out what it is. So let's remove that last line. and expand. This is how I like to do 3 by 3s. 1, 2, 4, and 0, 2, 3. Okay. First do your down diagonal. That's going to be 2, right? Next diagonal is 0. Next diagonal is 6. Okay. And let's do the up diagonals. That's -8. Next up diagonal is -3. And the last up diagonal is 0. Okay. My pen drug there, sorry. Oops. Alright, I didn't need to write the +0. That's what my pen was dragging. So Daniel's here. Alright. Now, I went over with Terrell the announcements, so you have to listen to YouTube to get them. But what I forgot to go over with Terrell, and I now remember, is just a quick review of our status here. And this, of course, one of my best classes of all time, with 7 students enrolled. One has turned in a research paper. 1 out of 7. Not an outstanding percentage, okay, out of such an outstanding class. Test 1, 4 out of 7 have done test 1, meaning 3, almost half the class, has not done test 1. Test 2, 3 out of 7 have done test 2, which means more than half the class have not turned in test 2. And today I'm giving you test 3. So that puts you behind either 1, 2, or 3 tests with just over a week left. In fact, at the end of the day, 1 week left in the term. 1 weekend left in the term. Okay? So, good deal. Okay. And since I will be giving, this is differential equations.
Yeah. Okay. I think I turned in linear algebra test 2.
What's that?
I believe I turned in linear algebra test 2.
Check and see. Yes, you did. Yes. All right. So just a word to the wise. And, of course, I'm announcing this to a class of 2 out of 7 of my best students of all time. Right? Okay. So I did my up diagonals, or down diagonals and my up diagonals, and came out with -11 plus, this is example 5 at the bottom of page 132. You get -11 plus 8, so that's going to be -3, right? And 1/2 of -3, or plus or minus, what do we use? Minus, so we'll become a plus. -1/2 times that would be +3/2. So that should be the area of that triangle, 3/2. And that's what the book got to. Okay? Make sense? Now.
So after we get the -3, that's what we'll figure out whether we use plus or minus, right? Versus 8 equals plus or minus 7.
Okay. Are you talking about this?
The other.
This here? Yeah. That's why you use the minus. Because your area is always positive.
So
because the determinant was this. If you had flipped these 2 rows and put 2, 2, 1, 1, 0, 1, and then left the other one the same, you've done your determinant, you would have gotten 3, positive 3. Because when you flip 2 rows, that gives you. So it's just the chance of the draw, whether you flip the rows or not, whether you get a plus or minus, the area is still going to be the same, but it's always going to be positive. Okay. So that came out 3/2. Now, what if they had given us 3 points? In fact, the same 3 points, except the first one they gave us as a 0, 1. rather than 1, 0. Okay? Now, when you do that determinant, you'll find out it comes out being 0. What does that mean? That those 3 points are all in the same line. They're not form a triangle. They are all collinear. So for that to be a 0 would mean it's a straight line. Now, a straight line, of course, has a 0 area because it's this length but 0 width. So, yeah. So if you ever get that determinant being 0, then you know those lines are collinear. Now, when you go to bigger shapes that we're going to, any 2 lines that are collinear will also produce the same thing. But, all right. Now, I guess we ought to do that, so let's do it quickly. Let's do that determinant that we get when we do 0, 1, 1, 2, 2, 1, 4, 3, 1. And expand the first 2, 0, 2, 4, and 1, 2, 3. Is that really what we had? No. 1, 2, 4. No, yeah. We didn't have it before because we swapped them. Yeah, so now it's 1, 2, 3. So now let's do our determinant. 0, 4, plus 6, up diagonals, minus 8. Y'all awake yet? Okay, good. Okay, that gave you a 0, and then we have a minus 2. And look at that. 10 minus 10 is 0. And sure enough, if you plotted those points on a decent piece of graph paper, and I think I'll pretend that I have one, like right there. Was it that special? Okay. 0, 1 would be right there. 2, 2 would be right there. And 4, 3 would be right there. Sure enough, those are all in the same line. Area 0. Okay? So, all right. So, guess what we have? Now we have a test for collinear points in the xy plane. If you have 3 points, let's go to a clean slide. If you just happen to have 3 points, x1, y1, x2, y2, x3, y3, okay, 3 points in the plane. They are collinear if and only if that determinant of x1, y1, 1, x2, y2, 1, x3, y3, 1, if that determinant is equal to 0. Okay? That's the only way those will be collinear. But you know, before now, I didn't have a way except graphing them to see if they're collinear. And sometimes even graphing them, if you got my lousy looking graphs, is that quite right or not? You know, now we know exactly, precisely what to do if that determinant is 0. All right. Now that test that we just got from the area thing, that test for collinear points can be adapted to another use. So here's another possibility. That is, when you are given 2 points in the xy plane, you can find an equation of the line passing through the points as follows. Okay? Here you have 2 points, x1, y1, and x2, y2. Okay? All right. So if we had a determinant Now this time the top is not going to be x1, y1. It's going to be x, y1. Then you put your x1, y1, 1, and your x2, y2, 1. Those are the 2 points. So if you want the equation going through those 2 points, do the determinant. Okay? What we'll do is expand that one time. Okay? X, x1, x2, y, y1, y2. Okay? And then do this, and that gives you y1x plus x2y plus x1, y2. Oh man, I'm having trouble breathing. Okay, and this will be plus x2, y1. Nope, minus, you're absolutely right. Good catch. Minus x2, y1. Minus y2x minus x1y, and here is then what you've got. Add all those together, you get y1 minus y2 times x1 plus x2 minus x1 . Goodness, my writing stinks. That is a y, but it's an ugly y. Sorry. I know those sounds on the recording are awful. Okay. Yep. Okay. Is equal to, I'm just going to put it on the other side, x2, y1 minus x1, y2. I just moved it on the other side. So here we have some number x. That's not a 1, that's just an x. Goodness gracious, where did that come from? Where did that line come from? Okay. Yeah. This number x plus that number y is equal to that number. Those are just numbers. We know the entity. There's the equation of the line that goes through those 2 points. Guaranteed. Okay? So there's another application of the determinant. Find the equation of the line if you know 2 points in the xy plane. Before that, you had to determine a slope, and then you had to do a point slope formula, and then you had to readjust and rearrange it to get it. Here you get it just like that. Okay. So let's do, I'm so sorry, my throat is gurgly. All right, let's do example 6. Find an equation that passes through 2 points. An equation of a line that passes through these 2 points, 2, 4, 1, 3. No, negative 1, 3. All right. So, we do our determinant. And how did that look? No, you put, it's our x, y, 1 is the top. It doesn't really matter, but this is how the book did it. Then you do 2, 4, 1, and then you do minus 1, 3, 1. Okay. Whew. I didn't mean to write that line in there, though typically you would, because I want to do my expansion. And that's going to be at x2 minus 1 and a y4, 3. Now, down diagonals give you 4x. Down diagonal gives you negative 1 y, or negative y. Okay? And plus 6. All right, let's do our up diagonal. You have 1 minus 1 minus sign, but you're doing a minus, so that would be a plus 4. Then your next up diagonal is a minus 3x, right? And then the next one is a minus 2y. Okay? Add those together, you get x minus 3y plus 10 is equal to 0. It's fine to leave it that way, or you could write it x minus 3y is equal to negative 10. Okay. Goodness gracious. And that's what they got too. X minus 3y is equal to negative 10. Now, my head is just clogged up like crazy. Let's just check and see. 2 minus 12 is minus 10. Minus 1 minus 9 is minus 10. Yeah, both of those points are on that line. It's real easy to check. Okay. Equation of a line, pretty simple. Didn't have to calculate a slope, didn't have to do a point slope formula, just plug it in. Okay. Now, if that was true for spatial things, remember we started with 3 points on a plane, area of a triangle, unless, of course, the 3 points are collinear, and if they are collinear, that means their determinant is 0. Well, that gave us a test to see if 3 points are collinear, and then that gave us a way to come up with the equation of a line. So starting with one thing, we got 2 other results. Well, now we're going to go to 3 dimensions. Yay! Okay. The formula for the area of a triangle in a plane has a straightforward generalization to a 3-dimensional space, which is presented without proof. Thank you so much. And here it is. The volume of a tetrahedron with vertices, now these are spatial vertices, x1, y1, z1, x2, y2, z2, x3, y3, z3, and x4, y4, z4. 3 points. One here, one there, and one down there. Okay? That forms a 4-sided figure, tetrahedron. Okay? Now, we want to do the volume of the tetrahedron. Okay? The volume of the tetrahedron would then be plus or minus, just in case you get them out of order and it comes out a negative determinant, 1/6, not 1/2, 1/6. Okay? Can't quite tell you why that's the case. The determinant formed by x1, y1, z1, guess what next? 1. x2, y2, z2, 1. x3, y3, z3, 1. x4, y4, z4, 1. Now this is, so far, the first term that I haven't been real tempted, I'm still tempted, but I've caught myself at times, to say x1, y1, z1, 1, x2, y2, z2, 2. No, you don't put it. It's 1. Those last ones are always 1. Okay. So, where the plus or minus sign is chosen just to give you a positive volume. You can't have a negative volume. I don't even know what that looks like. All right, so with that in mind, let's see if we can find the volume of a random mole tetrahedron. Okay? Find the volume of a tetrahedron whose vertices are 0, 4, 1, 4, 0, 0. I'm liking this one okay. 3, 5, 2. And 2, 2, 5. Now, I kind of hate this. We got a few zeros in there, meaning you're right on the edge of the first octet, but everything else is positive. So it keeps you in the first octet. I'm almost certain this works wherever you are. So, but so was about the area of a triangle. They just showed it in the first quadrant. So I can't guarantee you that it's going to work, but it seems like mentally it should work. Maybe not, though, so we'll see. All right. But we won't see on this one because this is in the first octave. Okay. Oh, my goodness. Looky here. Muhammad is here. Okay. All right. We're trying to find the volume of the tetrahedron that you get with those 4 points as your vertices. Application of determinants. So the volume is plus or minus. You only have that so you always have a positive volume. 1 over 6. Can't quite tell you why that's true, but it is. And then you put down these coordinates. 0, 4, 1. And always follow, the last column is always going to be a 1. Okay? 4, second? It works. Okay? 4, 0, 0, 1. 3, 5, 2, 1. And 2, 2, 5, 1. Okay. You have to have a 4 by 4, right? You have to have a square matrix to do a determinant. So that's maybe one reason, but why 1? Not real clear. But
okay, if you had only 3 coordinates, so you don't have to add them.
Okay, if you had what?
You have only 3 points.
3 points, then you don't have a tetrahedron. This is the volume of a tetrahedron. So you have to have 4 points on a tetrahedron. Have to. Okay. Otherwise, you have a plain triangle, and you can't do a volume of a triangle because it has no third dimension. Third dimension. Okay. So let's do it now. The bad news here: you don't have a special rule for doing this, so you do whatever works. Remember, easiest to pick the row or column with the most zeros. All right, so we'll pick this one. So let's start with the 4 here. We'll wipe out that row and that column. Okay. Now, plus or minus, I can't write, 1, 6, and let's do our business here. This 4 is in a negative position, so it's going to be a negative 4 times the determinant that's left over. 4, 1, 1, 5, 2, 1, 2, 5, 1. Okay? Then we also wipe out this one. Okay? same horizontal. And that's in a plus, minus, plus, minus, plus position. So it's plus 1 times the determinant of what's left. And that's a 0, 4, 1, 3, 5, 2, 2, 2, 5. Okay. Now, I wish I had thought I had a little better, but I didn't. So I'm going to take this one right here, 4, 1, 1, 5, 2, 1, 2, 5, 1, and repeat the first two columns, 4, 5, 2, and 1, 2, 5. Okay. What's that? Okay. I'm trying to do the determinant of this matrix here. Now, the easiest way for me to do a 3 by 3 is to repeat the first two columns and then do our diagonals. That's easier than trying to do it the other way, in my mind. Okay, so let's do our down diagonals, and that's going to be 8 plus 2 plus 25, right?
What's the last number?
5, sorry, this 5 here. My writing just kept getting smaller, I'm not sure why. Okay, then we do the up diagonals, minus 4. What's that? One times 5 times 5, 25. Right. Up diagonal is minus 4, minus 20, minus 5. Okay? Bless you. Okay, these are minus 25, that's a plus 25. This is a 10 minus 4, which is 6. So that is 6. Let's do the same thing for this one. That is a 0. It's an ugly 0. 0, 4, 1, 0, 4. I'm just going to write it this way. Huh? 0. It's that one. Okay. Next is a 3, 5, 2, 3, 5. And a 2, 2, 5, 2, 2. Okay. Now we're going to do its diagonal. 0, 16, plus 6, minus 10, 0, whoa, minus 60, I believe it is. Okay, so that's 22 minus 70 is 48, negative 48. So that's a negative 48. All right. All right. So what we have is plus or minus. I know which one I'm going to use. And here you have minus 24 minus 48. So that's going to be a minus 1/6 times,
Why you choose the negative number?
because your volumes have to be positive. And that's what you're looking for, a volume. Whatever the other is, you make that the same. Huh? Yeah. Okay. And this adds to 72. 6 will go into 72. Well, minus 7 minus is plus 12. So that has a volume of 12, I think. Yes, it does. 12 cubic units. So that's how you do the volume of a tetrahedron if you know the 4 vertices of a tetrahedron. Now, just like we did, except we're out of time, aren't we? Yes. Sorry about that. Okay, we will pick up tests for coplanar points in space. That's where we'll pick up for next time. Okay, and that means I'll put my paper here And we came close, awfully close to finishing 3.4. So homework exercises here, any of the odds 1 through 7, they're all at Calc Chat. 9 is a proof. You can do that if you like. It should be at Calc Chat 2. 11 is a proof. You should be able to do that if you want to. It's a Calc Chat. 13 is an illustration thing. Do that if you'd like. It's a Calc Chat. 15 is a proof. You can do that if you like. It's a should be a Calc Chat. Do any of the odds 17 to 29. They should all be a Calc Chat. Any of the odds 31 through 30, either 31 or 33, they both should be at Calc Chat. 35 should be at Calc Chat. 37 or 39 should be at Calc Chat. Any of the odds 41, either 41 or 43 should be at Calc Chat. 45 or 47 should be at Calc Chat. Volume of tetrahedron 49 or 51, they should be at Calc Chat. Stop there. We'll pick up the rest of those next time. Now, we didn't quite finish Chapter 3. We've got less than a page to go. Oh, no, just over a page to go. One example at the bottom, test at the bottom of one page, and then one more page, and that's it. So what I wanted to do, since y'all have been so good about it, I want to go and give you the third test. Okay? And this, try to get this back to me next week. Okay? Now, well, let's wait a minute. Let's think about this. We've only got 2 more classes, Tuesday and Thursday of next week. Let's say this be your final exam. Okay? And next week we are going to cover some more material, because if you do go somewhere for your next 2 years that you do need linear algebra, you're going to need to know something about vector spaces. And that's the next chapter. So we'll cover vector spaces as much as we can. When we finish this on Tuesday, then we'll start on vector spaces on Tuesday. We'll get as far as we can. If we get far enough that it's worth the test, I'll give it to you, but my guess is we won't. So this will probably be your last test. But I bet you're going to need to know something about vector spaces when you get to any course that depends on linear algebra. So we'll cover as much as we can on vector spaces next week. Okay? And that gives you time to finish your other tests and your research papers in all the classes. Okay? You got a week left, folks, and that's all. That's it, folks. Okay. So, good deal. Any questions?
You say find A. What you mean find A?
I can't hear you.
Number 3 say find A.
Number 2 says
Find A.
mine. Number 2 says determine which property of determinants. Number 3. It says find the determinant of A. There. There's vertical lines being determinant. Okay? There's a matrix.
Okay. Oh, I see. A, B, and C. A, B, C, and D. Part A, part B, and part C. Okay. Yes, I was like, find. I thought you were saying like find the factor of A times the.
Talking about the lowercase a that's in parentheses.
Yeah, that's.
That little a of mine, that corresponds to this answer. This little b corresponds to that answer. A, B, you actually write out the product, and then you do the determinant of that product.
So we want to find the determinant on this.
I'm sorry?
This question is only asking us for the determinant.
It deals with the C part has no determinants in it, but you have to get C to do the D part. C is just multiplying 2 matrices together to get another matrix. So I put the matrix there for you to fill in the blanks. Okay? Good deal. All right.
Dr. some good topics like mathematicians for linear algebra.
Okay. Okay. We have hit in just about every section a linear algebra applied, as in on page 135 of the thing, the Kepler's first law of planetary motion uses determinants. Okay? You can use determinants to find that. Every section has had, I think, has one of those little blurbs in it. So, Sudoku, the game Sudoku. Yeah. That's made up by determinant, or not determinants, matrices. Matrices. Yeah. And we hit several people. For instance, this time we had Rowan Hamilton. There's a potential paper topic right there. We had Kramer's rule. Kramer. We did that last time and this time.
I don't like Kramer.
Okay. I don't think he likes you either, but anyway. Okay.
Because he made life harder for me.
Okay. So there's just all sorts of possible examples. Listen to just about any class, and usually one or two pops up in every class. The possibilities there.
How about for differential equation? What's the other topic? What are good topics?
Okay, I can't hear you.
How about for differential equation? How about for differential equation?
Differential equation?
Yes.
Oh my goodness. We hit several people, if I remember right. Well, just about anything you deal with it comes from a differential equation. Mixture problems, stoichiometry in chemistry comes from that. There's just anything that has a rate in it. That's a derivative, okay? And you're basically solving differential equations. And I was trying to think some of the people we've run into. Wronski came up with the Wronskian that we use to determine linearity, or if things are independence, not linearity, but dependent or independent vectors, things like that. So there's several possibilities there.
See you Tuesday.
Okay. A little late in the term to be asking that question, but
I had a list, but it's not working out. It's not working out fine.
I see. Okay.
They make it life harder for me.
Well, this is a sad song, isn't it?
I know. I know who wrote it.
Yeah. I think I know who wrote it.
I'm just singing it. You wrote it.